Thank you, Sudeep. I love all this PR when I'm simply introducing Eric, so it's really pretty fantastic. As Sudeep outlined, and I'll make this short, virtually nothing in our society at this point hasn't been affected by AI. Transportation, go on and on about that, industrial robots, and what we did in PCAST was recently, about 3 months ago, we published a report, time flies, on AI, and you could look that up under PCAST reports. It's called Supercharging Research, Harnessing AI for the Betterment of Society. And so our charge was really, as science and technology people, to not worry about mitigation, but mostly about why we need to do this, because if we don't, we'll be left behind. So it really is a new era in science. So I'm very, very pleased to introduce my colleague in PCAST, Eric Horvitz. And I'll just tell you that one of the great things about being on PCAST is hoping that some of his knowledge and understanding gets to me by osmosis. There's nothing that he doesn't know or do. He's a leading researcher in AI in many, many wide variety of issues, and he's also Microsoft's Chief Science Officer. He really worries about societal changes, history, and how to impart AI in every aspect of society, including long-term bioinformatics and our healthcare systems. He has had many, many awards. I'm not going to go into that right now. I just want to introduce Eric Horvitz, and I'm really excited about this Omenn lecture. So let's all thank Eric.
Well, good morning. It's an honor to be here to deliver the Omenn Grand Challenges Address. So I've been immersed in AI research since 1984 when I kicked off my graduate work at Stanford University in AI. It's been an exhilarating ride, witnessing and contributing to the evolution of AI through its different paradigms over the decades. Let me just start from scratch. As a field, I view AI as the study of computational mechanisms underlying thought and intelligent behavior. Now, in a document that kicked off the modern study of AI, the founders of the field said that they were trying to find how to make machines solve kinds of problems now reserved for humans. Interesting definition of what they were trying to do. So we've seen an acceleration of capabilities over the last 20 years. I'd say looking back to like about 2000 or so, and AI technologies are now quite poised to influence so many areas of our lives. And they're already showing promise in areas like education, healthcare, and the sciences. Now, I believe that AI will come to be known as a key socio-technical leap forward for people in society. It'll come to stand alongside other major advances like electricity, the telephone, and flight. So given my sense of where things are going, I believe that 500 years from now, looking back from that point, the next 50 years will be remembered as a significant time of an upswing in AI innovation and influence. The period of time will likely be specially named. I'm not sure what the name will be. Now, we reached an inflection point in AI, and we've been riding on top of a fast-moving wave of innovation with deep neural network models for nearly 15 years now. And that wave has included reaching parity with humans on a number of challenging benchmarks, typically in the language and visual tasks. Now, about a decade ago, we started seeing the power of neural network models for applications like image-based diagnosis in medicine, spanning dermatology and radiology. And these were running at expert levels for these tasks. Of course, these don't necessarily mean that radiologists or dermatologists go away, but that piece of recognizing patterns was being matched by these systems. Now, we've seen multiple advances, including with the core representations that are used in AI, moving from linear sequences, like text, as indicated by that little line there, to two-dimensional representations that characterize images, to more general graph-theoretic representations, such as this graph that captures interactions among proteins in a yeast cell. But over the last 3 years, we've been riding on yet another acceleration that I see as an inflection upon an inflection. With the qualitative and quantitative capabilities we're now seeing with what's called generative AI, that's showing us unexpected powers of generation, synthesis, and composition. And these generative models are showing surprising powers that we still don't understand, which was interesting as AI experts. Now, many folks' first exposure to these generative powers came via image synthesis. When DALL-E 2 from OpenAI became available, some of the first queries that I explored was about visualizing and reflecting on a home project. I wanted to combine together solar panels for electricity and solar heating pads for keeping a pool warm. We were planning on a pool then. We've since abandoned that idea. Now, when I entered the prompt on solar cells affixed to solar heat collectors for heating a pool, back then I was surprised at the power of the compositional powers of these systems to bring together two concepts that had heretofore been unknown quite smoothly and realistically. The methods were clearly tools for stimulating the imagination and perhaps even scientific and engineering imagination, showing, for example, rich compositions for running water for heating through a solar cell array that had never been created before. Now, soon after, powers of generation were demonstrated for computer programming. One of the earliest and significant commercial successes of generative AI was the GitHub Copilot, which continues to generate guesses of the next portion of programming code that a software engineer may find useful. Now, GitHub Copilot today plays a significant role in the daily life of millions of software engineers. Studies have demonstrated the tool increases productivity of software engineers by over 50%, several different studies, when compared to control groups that do not use the Copilot, based on measures like the number of lines of code written, for example. Now, I've been particularly excited about interesting, and I still say mysterious, emergent capabilities we've been seeing with the scale, that come with the scale of data and compute. Now, indeed, the headline over the last 18 months or so that's been driving a great deal of excitement at airports and with our mother-in-laws and father-in-laws has been with the qualitative and quantitative capabilities we're seeing with these generative AI models that come with scale. Now, here's the data center where GPT-4 was birthed. It's just west of Des Moines, Iowa, that provides 10,000 top-line GPUs and 300,000 CPUs and very fast network. The models that came out of that data center are demonstrating the fast rise of capabilities in language, mathematics, and programming with computation and data, and with the emergence of surprising abilities like learning to solve a new task from a handful of examples in a single interaction. Now, in the fall of 2022, our team gained early access in August to test GPT-4 for studies of both safety and its capabilities. We were surprised by the general purpose powers of the model, for example, showing the ability to write a proof of the infinitude of primes as a poem, or to write computer programs in response to a prompt without specialized training. Imagine how we felt as engineers saying, like, wait a minute, this is like mind-blowing was our word, the words we used. The system seemed polymathic, and it was clearly a phase transition from the previous version of the same model, essentially, with the same techniques. Here's another example. We were impressed with the ability to see effective responses to long, detailed prompts, such as this prompt here, looking at doing a complex visualization task with a lot of data. And much now is being done with these and other large generative models, but deeper impact on the horizon. So it's still early, it's still very early days, but I see the rise of powerful automated reasoning capabilities and interesting and shared methods and pipelines being developed across multiple disciplines and challenge problems. And I'm particularly optimistic about possibilities ahead for harnessing AI to help scientists and engineers to make significant progress on global challenges. Now, long-standing grand challenges of what might be possible might come to fruition in areas spanning the health and life sciences, material science, agriculture, sustainability and climate science, the social sciences, and education. So I'd like to turn now to the possibilities for harnessing the rising powers of AI to help solve grand challenges in the realm of scientific discovery. As Laura mentioned, the possibilities for leveraging AI to meet global challenges was the focus of a report from the AI Working Group of the President's Council of Advisors on Science and Technology that I serve on with Laura. The report was released just this past spring. I very much enjoyed serving on that working group along with Laura and her co-chair, Terrence Tao. They did a fabulous job co-chairing this study. And so I refer, as Laura did, the audience to that report, and I'll highlight and extend ideas in the report here this morning. So AI is in the early days of helping scientists with modeling and reasoning and with performing scientific discovery at multiple spatial and temporal scales. Neural network models are now under development for spatial scales ranging from atoms to compounds, from gene expression and protein interactions to cellular networks of proteins and their interactions, from cells to human physiology, and from individuals to populations. A constellation of interrelated AI methods show promise for helping to supercharge what I would call core components of scientific discovery, including helping to generate and identify candidate solutions in big combinatorial spaces, to accelerate and enhance scientific models and simulations, to analyze new types of data, to bridge, this particularly excites me, to bridge in silico the world of computing with the natural by guiding experimentation and choosing where and when to run complex and expensive wet lab experiments. And perhaps most importantly, to elucidate mechanisms and to provide insights, new knowledge. So I want to give you a few examples today that highlights possibilities and go a little bit more into detail here to give you a feel for where things are in the sciences. The first is in the realm of material science, the area of science and technology that Laura heralds from, that provides us with novel substances and materials. You know, materials are absolutely essential in our lives. To highlight the essentiality of materials, we've even used the name of materials to label the level of advancement of human civilizations: the Stone Age, the Bronze Age, the Iron Age, and so on. Recently, AI methods have come to be used to find new materials, particularly to help material scientists to cut through large spaces of possibilities to identify candidate materials. And we're on the path now to achieving breakthroughs in these material science with these challenge problems, including hard problems of finding new ways to store energy available from intermittent sources, which is one of the big problems with using solar and wind, to find new catalysts, such as those that can perform less expensive carbon capture, and even achieving long-pursued dreams of room temperature superconductors, which would be absolutely game-changing for humanity, and I'm sure Laura will be involved in that discovery should it happen in our lifetimes. So properties of materials in the world of material science are largely defined by complex interactions among the electron shells of molecules. And the best understandings we have of electron locations and interactions in substances comes via Schrodinger's equation, which dictates the distribution, or the probabilistic distribution of positions of electrons in space. Now, solving Schrodinger's equation is exponential in the number of electrons, and that makes its direct use untenable as a tool for searching through massive numbers of possibilities when it comes to thinking through new materials. But approximate methods have been developed that are more efficient, but they're still challenging to compute and use. But recently, AI models have been built to serve as what I would call Schrodinger simulators of sorts. They're trained via more complex classic computations on sample molecules you see on the left there. And then while they're somewhat expensive to build, once built, these models can be used to make predictions thousands of times faster than the base level computations. That's the way AI is being used in these systems for material science. Now, these neural approximation models are made more powerful when they take into consideration laws of physics, foundational principles of invariance and equivariance. We can talk more about that in Q&A. And we can use these models in end-to-end scientific discovery pipelines and workflows. Scientific communities are learning about how to build and use these pipelines now. And in the material sciences, training and inference workflows are being used to generate and then evaluate vast pools of promising candidates. Now, more generally, there's excitement about building what are being called these large science foundation models that can be used for multiple tasks within and across scientific disciplines The goal is to build these foundation models that have multiple types of scientific knowledge weaved together inside of them, and to press them into service to help with synthesis of ideas as well as with the elucidation of new insights. And different architectures are being explored for these, what I would call multidimensional or multimodal scientific models that are being built right now. So as an example of an AI-centric discovery pipeline, and I want to just point this out because it makes things a little bit more concrete, I'll give a recent collaboration between the Department of Energy's Pacific Northwest National Laboratory, PNNL, and Microsoft, where a materials discovery pipeline was harnessed to build and to identify a promising new electrolyte candidate for a battery, one that requires 70% less lithium than today's batteries. The pipeline employs several distinct phases of AI models and different kinds of models, as opposed to one model, as well as weaving in traditional high-performance computing to first generate a list of 32 million possibilities, looking at different ways electrolytes, metal atoms can sit together with other atoms for a new battery, and then to narrow down the list to 500,000 stable materials, then to further focus down the list to 18 promising new candidates. In the end, a solution is identified, then synthesized and tested. Real batteries running with, we would not have discovered. We would have maybe, let me just say that, components of the discovery pipeline operated at speeds thousands of times faster than traditional methods. So the team estimates that achieving the same result would have taken more than 20 years and cost nearly $2 billion with classical methods. But with the power of the new workflow, the breakthrough happened in 80 hours with a market cost of roughly $350,000, with a speed 2,000 times faster at less than 1% of the cost. So I take these methods as illustrative of what's posed to happen in multiple fields. I'd like to now move on to highlight possibilities for AI-powered discoveries in the health and life sciences. In this area, AI models are already being used to perform expert-level diagnosis, as I mentioned earlier, to, in very well-celebrated breakthroughs, predict the structure of proteins from their sequences, to predict protein interactions, which moves from structure to function, which is very exciting. They're also providing protein design tools for vaccines and therapies, such as blocking the binding regions of viruses, particularly for COVID, most recently. So I see us making significant progress in this space on grand challenges in the health and life sciences over the next decade, which include developing truly custom-tailored cancer therapies, disrupting Alzheimer's disease, mitigating autoimmune disorders, and prolonging the vibrancy of cells. Science magazine celebrated the prediction of protein structure from amino acids as the 2021 breakthrough of the year. And I have to agree with David Baker here, who we've worked closely with at University of Washington as one of the key contributors, and someone noted in that prize that year, along with the DeepMind team, that all areas of computational and molecular biology will be transformed by these methods. Now, the DeepMind team in London computed thousands of predicted structures that cover over 98% of the human proteome, all of our proteins, when prior to this work, only 17% of the structures were known. Now, on the left side of this slide here, I show the structure of one of the proteins that was identified by the London team, where the red circle highlights structural changes that occur with a mutation that demonstrates the foundations of a rare neurodegenerative disease named Wolfram syndrome. On the right side, showing work at the University of Washington in David Baker's lab that comes to understandings about the protein interactome to automatically identify which proteins likely interact with others that led biologists to say, put names on these things, these processes they were thought to be part of. I should say that and this work was done in a eukaryotic cousin of the cells that we are composed of, in yeast. I call out in the red circle there to highlight this magical label of unknown. Isn't that beautiful that the AI system has pointed us at some dark matter? We don't know what's going on when those two proteins interact, but it's telling us they likely interact. In another area of effort, generative AI methods are leading to stunning results with designing new proteins, these proteins that are designed to fold to a specific target structure and function, and hopefully function. These design tools employ, believe it or not, similar methods to those used in image generation tools like DALL-E. Words like in-painting are used to describe them. When I talk to David, for example, we're in-painting and out-painting and so on. These tools have been used to create new synthetic vaccine for COVID, many other directions right now. These were the tools that were used to create custom-tailored proteins that bind tightly to the receptor domain of COVID, stopping the virus cold. People are talking about a nasal spray with that right now. Also exciting are new biomedical discovery pipelines, which on the surface are not that different in spirit to the material science pipeline I just talked about. These new bioscience discovery pipelines have been harnessed to identify new kinds of antibiotics. You know, the work couldn't be more timely. In recent years, there's been a rapid emergence of antibiotic-resistant bacteria, and this has been exacerbated by the fact that our antibiotics work in the same way. There's a lack of fundamentally new mechanisms of operation, so bacteria are evolving around, our common methodologies that are the mechanisms, the common mechanisms. Global deaths due to resistant infections are projected to reach 10 million by the year 2050. So this frames the need for new antibiotics, and work over the years includes doing screening in wet labs. That's been the traditional approach. But the AI methods are enabling drug discovery to be performed largely in silico to allow exploration of much larger spaces. Scientists at MIT trained a neural network model with a couple of thousands of examples of molecules that they discovered in the lab through big screenings that showed antibacterial activity in the lab. They then aimed the model at multiple massive chemical libraries and discovered a molecule that they named halicin, believe it or not, in honor of Hal the computer from the movie 2001. Now, halicin has a structure quite distinct from conventional antibiotics and has a bactericidal activity against a wide spectrum of pathogens, including TB, C. difficile, and a challenging bacterial infection, A. Bomani. Research reveals, as the AI showed us this new structure and provided us with the ability to study this in the lab, that the compound operates through a very unconventional mechanism. It interferes with the electrochemical gradient across membranes. I put it in quotes in my mind when I read about this. It shorts out bacteria, just takes their energy away. New mechanism discovered by AI. And just last December, the same lab at MIT, the Collins lab, reported yet new discoveries with an antibiotic that can be used to kill methicillin-resistant Staph aureus, the infamous, for our healthcare people, the infamous MRSA infection. This team, in this case, took things a step further towards deeper scholarship, from my point of view, in that they used what they referred to as explainable AI to reveal new insights about the operation of novel antibiotic activity and about the space of candidate solutions represented by this cloud here. Now, another very exciting area in the health and life sciences is to build rich multimodal neural foundation models that bring together genomic, transcriptomic, which is what's being transcribed, proteomic, the protein structure and interactions, and phenotype information, patient symptoms and history, and so on, physical. These models are a promising approach to developing tools that can deliver what I've been calling ultra-personalized medicine, taking population data down to the foundations to apply to a single person's nuanced composition and history. this takes the aspirations of what we've been calling precision medicine to the next level, and I think we can get there. As an example of recent work, to make it a little bit more concrete, in building such multimodal models, a cross-organizational project named GigaPath just published last month in Nature the result of a project that's centered on training a multimodal model. I say multimodal meaning different forms of information being woven together by synchronizing the samples with over 150,000 pathology slides. They actually broke it into tiles to the level of billions of patches, but they also mapped and matched those images with genomic and cancer staging information. So the model showed how scale can boost performance on doing cancer subtyping and mutation prediction just from the imagery. So it just shows the power of where things are going. Now, I'll stop in talking about, that's a great stopping point, I think, about possibilities for advances in the health and life sciences with a longer-term challenge, and this is a dream, that's now come on the radar as feasible beyond glimmers via AI advances, and this is harnessing multimodal AI models to build virtual cells that provide high-fidelity in silico simulations of cellular biology. I've come out of meetings, in fact, it's a recent full-day meeting on this topic, in this case hosted by the CZI folks, pursuing this vision with colleagues. And I can report that the teams are armed with very concrete ideas on steps forward. This is not just a fancy image. So I provided some examples from health and life science and material science, but the power, methods, and excitement extends to other grand challenges. Advances in the core AI methods and pipelines being developed across multiple disciplines and challenge problems will be game-changing, and I'm very optimistic about the possibilities ahead. Before ending, I'd like to touch on, based on several important topics, I think that will sort of make things more, a little bit, bring things to life. The first is on the fast-paced evolution of tools for shaping and custom tailoring AI models in the sciences. So for folks who have been playing with GPT-4 and Claude and other models, large-scale language models, and we're seeing magical performance in these interactive engagements, should know that behind the scenes, there's been a whole bunch of work on how we could harness the models by specializing and extending them. There's been innovation with prompting, with doing domain-specific fine-tuning, and with integrating with databases, retrieval augmented generation. Now, there's also the rise of frameworks that allow scientists and engineers to build more sophisticated problem solvers by defining sets of independent specialists or agents that can be orchestrated into larger multi-step planners and solvers. And these systems can take a complex problem, divide it up among multiple specialized agents, as they're called, and solve problems as a collaboration amongst themselves, sort of forming multi-agent systems. Here's an example that we've been calling the Biomedical Research Assistant, which is powered by 5 separate agents, including a bioscience research reviewer and an orchestrator. And just give you a sense for how this works here. Basically, in operation, the Biomedical Research Assistant collects and reads relevant literature, assesses scientific rigor of each paper and study, synthesizes a holistic report weighing evidence for the strength of the study, identifies contradictions and disputes, and then proposes steps forward with studies and experiments automatically. So to give you an idea, let's show you how this works here right now. Let me hop through here. Let me just highlight synthesis of a holistic report, identifying contradictions and disputes, and then proposing actual experiments. So it's amazing to watch these systems work. Here's an example. What is the role of telomere length in cellular aging and senescence? You basically point the system at the query, and it goes and reads PubMed. It figures out how to read PubMed articles. For each one, it files a report on assessing the scientific rigor of the report, multiple dimensions of the rigor. It considers the rigor and the content in fusing a comprehensive report together about answering this question. It identifies contradictions and disputes in multiple years of literature. And then it says, what can you do next? How can we resolve these disputes and contradictions, and how can we advance the field further? And then I'll mention here, moving beyond bespoke pipelines, a longer-term vision is to have AI systems play the role of tools that can serve as a partner in scientific reasoning, one that can complement or augment the scientist's own reasoning. About a year ago, even before GPT-4 came out, we published an article at the cover story of the Communications of the ACM with colleagues about possibilities for building AI cognitive agents for assisting scientists. And we called out multiple ways that systems might help further bolster aspects of a scientist's cognition, the kind of components of thinking that power scientific discovery. And I'm very bullish on possibilities, and I refer you to this story in last year's Communications of the ACM. But as part of that work, we did early informal explorations of GPT-4 as a general tool for helping scientists in an interactive way with reading and learning about new developments and so on. As an example, I remember back in December, I took brand new stories coming out in Nature and Science, and I had them digested by these large models, and I asked them questions of the form, if we assume that the author's hypothesis is incorrect, what else might be going on here? And looked at the answers coming back. Now, more recently, as part of exploration on the PCAST AI working group that I was doing with another member of the group, Nobel laureate Saul Perlmutter, we explored together how large language models might serve as mind-expanding tools for physics. Now, one example was we worked with a leader in the realm of quasicrystals. Quasicrystals are an aperiodic crystal that were first proposed mathematically as a new form of matter that hadn't been seen before, and then discovered in meteorites, and later pursued on the Earth. We asked the large language models to help with speculating about the base materials and energy sources that might lead to aluminum-based quasicrystals, and where might you find them on the Earth. The system suggested lightning bolts on bauxite mines, and even suggested where we might travel to search for these quasicrystals that were created in this way. Do you want tickets to Venezuela? Now, before closing, I'd like to just, we couldn't help, this is another talk in itself, to move from technical to socio-technical and to stress the importance of keeping a careful eye on enablement and on policy and responsibilities. We need to keep constant and vigilant watches on implications of the advances that we pursue. So beyond technical advances, we're going to have to attend to key socio-technical considerations to nurture the creative and vibrant uses of AI applications in the sciences. And these include efforts to ensure that scientists and engineers across sectors in the United States and other countries gain access to computing infrastructure, including computational resources, models and tools, and data sets and data hosting. We've been very active as a company in supporting the National AI Research Resource, the NAIR. It's in pilot phase right now. The pilot is a nice direction. I think we just started doing matching last week with proposals coming in. It's a very exciting time. We need to do more. We need to really fully fund the full NAIR in its full scope as it's been conceived. We also need to work on community to explore the pooling and sharing of resources required to achieve shared scientific goals. These include data resources, of course. Furthermore, we have to empower our scientists and engineers. That's going to require updating educational curricula to incorporate AI tools from K through 12 through higher education and graduate school within different disciplines. We have to work to seamlessly integrate these tools into these academic disciplines. to ensure that future scientists and workforce have appropriate training. It's also crucial to maintain scientific integrity with uses of AI applications. And so we're going to need special considerations to assure the veracity of inferences of these models, the replicability of results, tracking the provenance of data, and attribution of sources. For example, did this data here come from a model, or is it empirical from an experiment? We need to mark that data carefully. I refer people to a recent National Academies of Science Sunnyland study that was just published in the PNAS last month on these issues. This includes a call to create a standing body at NAS to track developments and to make recommendations on best practices over time. I enjoyed very much working with colleagues on those recommendations and then writing that paper on protecting scientific integrity in an era of generative AI. And lastly, and I think most importantly, we're going to have to prioritize investments in safety and responsibility, thinking through as best we can and taking proactive measures against potential misuses of the rising powers of AI. All great innovations in technology are dual use. The newfound powers and capabilities can always be used to achieve wonders, as they have for humanity, but they can also cause harm. And sometimes that harm comes via inadvertent, unplanned, or unexpected effects. Other times, unfortunately, via malevolent uses of the technologies and harnessing it in costly ways for humanity. So we need to be vigilant and do our best with considerations and mitigations of the downsides, such that we can better harness the beauty, the wonders, the human well-being, human flourishment that could come via new insights, new understandings, new technologies, while minimizing the costly outcomes and abuses. In the spirit of Gilbert, Omenn's intent for this named lecture, it's going to be really important to keep a steady and unwavering and intensive focus on addressing grand challenges. And doing this will take leveraging sets of AI innovations, not just the latest, shiniest tools. There's a rich constellation of AI technologies that I've grown up with and contributed to over decades. So we're truly only at the foothills of an AI era in the sciences, but nonetheless, we can already see beyond the beautiful rolling foothills through the mist out to the exciting future ahead. Thanks for your attention. I think we have some time for some questions.